All right, so let's finish the lecture about sequence alignment, which is just the theoretical part about it. I told you about the different types, right? I told you can compare just two different alignments or two different sequences, and computer scientists call those strings. So they're like strings of characters attached, right? So it's a um, bunch of letters. In this case, could be ATCs, no, ATCs and Gs for DNA, or amino acids for protein. Or you can do multiple sequence. And then the global versus local, it depends on your goal. But in general, the tools you're going to use BLAST, which does local. The L in BLAST stands for local. And you guys are going to use a bioinformatics tool that does multiple sequence alignment, that when you are looking many sequences, what do they have in common? Then you often want to see how do they resemble each other overall. So the multiple sequence alignment tool does global alignment. So which tool to use depends on, are you looking for blocks or for overall similarity, blocks of similarity or overall? And are you comparing just two sequences? In which case, could you do either one of these? Or are you looking overall multiple sequences? And you might wonder, how about if I want local alignment of multiple sequences? Then there are some tweaks you'd have to do. In the class, I don't actually go over that. When I ask you to compare many of them, you're just going to run global. All right, so I'm going to actually jump to an example of alignment and then move on to amino acid substitution matrices. I give an example of one. There are, okay, two main ones, but one main one, the one that I go into more detail, is the one that is the default in alignment programs. It's called BLOSUM62. And this, the reasoning behind this course, that's the part that I want you to stare at stuff and then figure out what's the pattern that I see here. All right, so skipping to the end because you do not want to see each of these things again. All right, so this is the a consensus sequence that I was showing you. Maybe it's this one or this one. So it's the same alignment, which is in here. I was emphasizing that the consensus sequences where these amino acids agree, and they don't always agree. So these are aspartic acid and asparagine in here. So then there is some symbol that they used for that are standard symbols for whenever there is a substitution. These two are pretty similar. And then whenever they agree exactly the same, all of these are serine, then you put an S there. So it's like everybody chose that same topping. So that's, and then the sequence on the bottom is the pizza that you're ordering, right? It's where people agreed. Okay, so when we are looking at this alignment, not only is there the consensus sequence on the bottom, we also see that some amino acids change. So for whatever this sample is, there was a serine there, but then this other sample, probably different place in China, who knows, different amino acid. So there was a substitution there. I like to think about this as, this is some tower of Jenga. You know that game that you can remove some part and hope it doesn't fall? This one would be another tower. So it's kind of modification of Jenga. In this case, you had a serine on the tower. You removed the serine and then you put an asparagine in its place. And the tower falling would be analogous to this protein doesn't hold the structure. So when that happens, when that substitution happens, and the protein doesn't hold the structure, then if that protein is essential for the organism to survive, then that organism will die or will be less fit. And then, so let's say that this one, the N, makes this protein, whatever this thing is here, less stable than the S. So then you would expect the S to be more frequent because the protein is more stable, and let's say it's a protein that the organism needs. So you'd like that protein to not fall apart. You'd like your Jenga tower to not be like, wobbly. And in this one, it's wobbly. The tower hasn't fallen. Oh, the tower has not fallen yet, because if it had fallen, that would mean that this died, and then it wouldn't exist in the population. And it could just be that by chance is less often, maybe has nothing to do with fitness. So I don't think I actually go over this topic too much, but if you study more like evolution, then you'd see there's like genetic drift, there's like other influences. It's not just this is a better amino acid for this position than this. Maybe it's just lucky, or who knows. All right, so this is the amino acid substitution is what I was showing you in the alignment, which for that one position in the protein, maybe you have a different amino acid. And that substitution either does nothing to the structure or the function of the protein, or it does something. So either that change is neutral, or that change is negative or positive, so neutral or not neutral. The substitution matrix, so matrix is a table, right? And it looks at how often does one amino acid substitute the other. So the substitution matrix is a score of probability of changing one amino acid into another. And when I say change, I don't mean in this one existing organism that the organism is going to remove one and substitute it by another one. I just mean there's a mutation in DNA that will encode a different amino acid, and then a different amino acid shows up in the protein. And that's what I mean by one amino acid changing to another. It's not that the amino acid itself transforms. It's just that there is a sequence in DNA that changes, that then encodes a different amino acid, and that's why you end up, let me go back. That's why you end up with like a different amino acid. So there's asparagine there. There's some DNA codon that encodes asparagine, and then there are mutations in DNA that encoded serine instead of asparagine. Okay, so it's not that the amino acid changed from being asparagine to being serine. It's just that the DNA changed, and therefore a different amino acid is encoded. So far so good. All right, good. All right, thanks for responding. So here's an example. As I told you, okay, this BLOSUM is the standard substitution matrix, amino acid substitution matrix that people use. There's actually blocks. That's what the BLOSUM is for. It's blocks substitution matrix. People just like coming up with cute acronyms. And these are husband and wife, as I was told. What they did was they looked at 2,000 blocks of alignment sequences, and they said, let's see how often one amino acid substitutes another one. So they looked at each pair substitution. Let's say they looked how often does a T substitute a C, and then they calculated what's the frequency of the observed, what's the frequency of expected. So you can think about that when you took genetics. You probably learned about like chi-square, which is, okay, at random, this is what you would expect. So let's say you have two flavors of ice cream. You have chocolate and you have, let's see one that's kind of weird. I don't know, nuts. And then you go like, okay, if you have two flavors of chocolate or two flavors of ice cream, you expect half of the people to choose one, half of the people to choose the other. That would be the expected substitution for randomness, right? So it's either one or the other at equal ratios. But then people are like, who wants nuts? Maybe I'm allergic to nuts or whatever. So there's a preference for chocolate. Then you would see a substitution. So not that too many people chose nut ice cream. Most of them chose chocolate. And then you're like, oh, there is a bias for substituting this one for the other. And it could be because of preference. It could be because, in this case, maybe fitness of the organism. Maybe you're allergic to nuts and then you don't eat that. You prefer something else. So anyway, they looked at what if there is no force playing a role to prefer one amino acid over the other? That's the randomness one. But then in reality, it's not that random, right? Some substitutions work better than others. Maybe you substituted chocolate by dark chocolate. No, it didn't change that much. And then maybe then it's close to the randomness one. And the calculated odds ratio, it's how often these things substitute one for the other in comparison if it was random versus if it's not random. And then these numbers here are the odds ratio, or they're the log of odds score, so that LOD score. All right, so then you look here and you're like, all right, what do these numbers mean? So the positive scores, it means that the substitution is more likely than chance. So, and it's not always a substitution, right? If you look, okay, which ones are the positive scores? Okay, there's like here, this is a positive score. So valine and isoleucine, and those two substitute each other more often than just chance. And then let's see what else. If you look at these ones that are really dark, then you're like, okay, let's look at an easy one here, right on top. Cysteine, substitute cysteine. So this, what this actually means is that there's no substitution. A cysteine tends, or this is the score for it to remain a cysteine. And so when you look here, you're like, ooh, 9 is kind of a big number in comparison to like these other ones. 7 is kind of big. That's like 4, 6, 5, 4, 6, 5, whatever. 7 is kind of large. 8 is a little large. 4, 5, boring. 6, 7, ooh, 11. So you look at these things and you go like, all right, so there must be some force to say this is important, right? That this thing is called the tryptophan. And you don't have to memorize these things. I just memorized it because, you know, I had to at one point. But you guys can Google it. Okay, this guy here is a high score, which means for tryptophan, to stay tryptophan, it happens very often, more often than chance. So if you think, okay, tryptophan could change for something else, yeah, it could, but it often doesn't change. That's what this high positive number means. So tryptophan is really special, and then another second special is cysteine, and then you're like, okay, then this one, proline, it's kind of special too, which is what we're going to look at in the next slide. But for now, what I wanted to know is, what is the substitution matrix? So that is this calculation of how often an amino acid has the propensity to stay the same, so to not substitute one amino acid, well, like one amino acid by another. And then you're going to see that there's a reason why some of them tend to stay the same and not change. And so the negative scores, the substitution is less likely than chance. So let's look at the negative scores. You're like, -3 kind of big, -4, that's kind of a serious, I think -4 might be the lowest score. And let's see, why is that so bad? So this is glutamic acid, substituting cysteine, and you're like, I don't know, looking at the table, I don't know, all I know is that glutamic acid and cysteine do not substitute each other very much. So it's less likely than chance. Let's see. I think that's all I wanted to note from this. Or maybe I'll introduce the idea of when you're calculating scores. You could interpret this also as this is you, and then this is the person that it's your candidate to be your mate. And then you're like, maybe this is something special about you. And if that person has that something special too, then you're like, ooh, I'm gonna give this person lots of points. And then here it's something that you like and they like different. And then you're like, okay, but in this position we already said we agree. So let's say in the second position, or maybe we'll go here. So you like alanine, he or she likes serine, and you're like, we don't really agree, but that's better than disagreeing. And then on this minus, it's like, whoa, you like this style of, okay, here, you like this style of music. My goodness, I cannot stand this style of music. If you're gonna be together, you're just going to have to not listen to music together or whatever. So think about these scores as when you're doing an alignment, which is you're comparing how two things agree. They're like, they really disagree. So it's going to drive a score of an alignment down. All right, so the way these are calculated is how often one amino acid is likely to substitute the other. And these scores here are used for when you are doing an alignment, you're checking how much do we agree, and if we have a lot in common, this alignment is going to have a high score. If we disagree in a lot of stuff, then the alignment is going to have a lower score, and then I will swipe you left, whatever, and then move on to the next alignment. All right, so far so good?
Yep, so far so good.
All right, thanks. So good. Thank you guys for answering. All right, so this is the part that I wanted you to stare at here, the amino acid structures. And I wanted to see, okay, I pointed out that cysteine is a high score for cysteine. And I pointed out like tryptophan has a high score for staying tryptophan. So I guess the easiest way to address this one is what's special about tryptophan and what's special about cysteine. And you're like, I don't know. So here, tryptophan is this guy here. And cysteine is this one here. So you can compare tryptophan to other stuff and see why is tryptophan special. Just think if this tryptophan was one piece of your Jenga tower, if you removed the tryptophan and substituted by other stuff, maybe you substitute by threonine, what's going to happen to Jenga tower? Yeah, good job. Right. So if you remove the tryptophan, it's like, oh, there's this gashing hole in my structure. I need to fill this void. And maybe I can fill the void with phenylalanine, but definitely tryptophan won't do it for me. So your Jenga tower will fall if you substitute tryptophan with some other amino acid that it's too much smaller. And God forbid you do like oxyglycine. Where's that one? Okay, alanine is really small too. So you want what's special about tryptophan? One of the things that is special is that it's really large. And then these guys that have these rings, they're special too. So normally they will tend to substitute by something that is like them. You know? Yes, Jackson.
Hi, I just have a quick general question. I think I missed this in the last slide, but what are the difference between the bold diagonal numbers and the numbers that are going down in the BLOSUM chart?
Okay, so the bold ones, these are what's the chance that the amino acid will stay the same. So you see the bold is always like on that diagonal. It's cysteine with cysteine, serine stays serine, threonine stays threonine. So it's proline stays proline. So the bold ones are the chance that the amino acid is going to remain the same. And as you can see, they are all positive, which means that the amino acids in each position, the protein, they tend to stay the same because through evolution, a lot of the changes that were bad were weeded out. And then the ones that are not bold, they are the ones when you are changing. So you're changing a cysteine by a serine, like we're not very good. And then, -1 means this change here is less likely to occur than randomness. So that means that this substitution here doesn't occur very often in nature. Maybe because your Jenga tower fell, maybe because it didn't fall, but the protein doesn't do what it should do. So the negative numbers, like I was trying to point out, this one -4, bad choice. There are other -4, but got it. So the bold
thank you.
ones are, you're welcome. Yeah, the bold ones are when the amino acid stays the same. There are positive ones, which is it's more likely than chance, even if you're changing the amino acids. So like tryptophan and this guy here is tyrosine. So when you go look like, oh, they must be similar in structure. So here's tyrosine, like, oh, I see why it's okay if you're going to remove a tryptophan to put a tyrosine in. Or maybe it was a tyrosine and now you're like, you removed that and you are jamming a bigger amino acid. But the fact that they are both hydrophobic side chains, so it matters if it's hydrophobic, if it's uncharged. It depends on their physical chemistry. That matters too, it's not just size. So it's size and the physical chemistry of the amino acid that matter. And yeah, so how about cysteine? Like those are my two favorite ones to point out because they are really special. So cysteine, what's special about that is this S here. It's the sulfur, and the S as in sulfur. So see this SH. What this allows is that this amino acid here is going to bind another amino acid by losing this hydrogen. So it makes a hydrogen bond with another amino acid, which toward the end of the semester, you're going to build a structure. And then the way to hold it together will be to put tape. And that would be those disulfide bonds. That's what's representing. So the cysteine, you could think about the cysteine as an amino acid that allows you to, you have this string. So actually, let me stop here for it. So suppose, I have a lot of string, but right now I just have this paper. So let's say this is your amino acid chain. There's like a bunch of beads here. Imagine that. And then this thing, it actually can either curl up like this, make like alpha helices, or it can fold like this. So let's say when it folds like this, it stays folded like this by different mechanisms, but you could think that if there is a cysteine here on the top, or my finger, let me put it like, okay, maybe there's a cysteine right here, and another cysteine right here. These two, they form a hydrogen bond. You could think, oh, there's a hydrogen bond there. Then it's like the tape that is holding this thing like this, rather than like, rather than opening. So that's what is special about the cysteine, is that sulfur. Yeah. Oh, it is not. That's not what I wanted. Good. Okay. All right. So what I was hoping you'd convey here, or maybe you put it on the chat. what is what is the reason why some numbers here, some LOD scores, the log of odds scores, are high and other ones are low? And I'd like you to tell me that in comparison to the structure of the amino acids. Maybe not in any particular case, but like in general, what pattern do you see?